Hey there, welcome to my video on nuclear energy. I love talking about nuclear energy because I really view it as the future of our planet and the solution to a lot of our problems. And let me tell you why. First, it's worth remembering that almost all of our energy on Earth comes from nuclear energy somehow. It's nuclear fusion that powers the sun. And the sun's photons drive photosynthesis, which makes plants, which makes all of our oil and gas, and all of our food. Likewise, those same photons can be harnessed directly as solar power, or they can heat the land to make wind. Essentially, if you trace any source of renewable energy back, it's going to lead you to nuclear processes. So why not just harvest nuclear energy directly? Centuries of scientific research have given us the ability to make electricity directly from nuclear decay and nuclear fission. So why aren't we doing more of this? Well, let's look at the risks and the benefits. We'll go with risks first. The big one is nuclear meltdowns, like the one that happened at Fukushima Daiichi in Japan in 2011. These meltdowns have the potential to spread radioactive elements around a large area and can be very difficult to clean up. In fact, Fukushima still hasn't been entirely cleaned up 7 years later. Likewise, nuclear energy generates waste, and that waste is long-lived and can present risks of leakage into groundwater, or those radioactive materials can fall into the hands of terrorists. So there's definitely some risks, but I would argue that the benefits far outweigh the risks. Imagine a limitless source of carbon-free energy. Instead of burning coal and churning CO2 into the atmosphere, we're making electricity without burning anything, no CO2. And we're making a lot of electricity. A single nuclear power plant, for example, the one that was recently decommissioned in Vermont, makes the equivalent of roughly 700 large wind turbines or roughly 1.3 million solar trackers. So a nuclear power plant is a big deal. And if we have this much energy, we can do anything. We can desalinate water. We can remove CO2 from the atmosphere. We can create unlimited amounts of fertilizer to grow food. That's why I'm convinced the future of humanity lies in nuclear energy. So in this video, I want to educate you a bit. What is nuclear fission that drives this process? What are the elements of a conventional nuclear reactor? And then I want to finish by looking at an example of a nuclear meltdown to talk about what happened and how those risks might be mitigated going forward. So, most nuclear reactors are driven by fission of uranium-235. And here's how this works. We start out with a neutron, and that neutron, if it's moving slowly enough, will be captured into the uranium-235 nucleus. The nucleus then destabilizes and splits, or fissions, into two separate pieces. When it does so, it releases a large amount of energy, okay? And as these fission fragments, which themselves are now new elements, like xenon or krypton, these fragments actually are moving fast and they dump their energy as heat. Another product of fission is additional neutrons, and this is really the key. These additional neutrons go on to drive subsequent fission reactions in other atoms of uranium. And this is where the idea of a nuclear chain reaction comes in. As long as each fission event makes multiple neutrons, we can actually spread those neutrons around and they can each go on to induce more fission, and we can get a chain reaction and produce a lot of energy. So that's the basis for how most energy is produced. Now let's look at what are the elements of a nuclear reactor. How do we harness and control nuclear fission? Well, we have actually four main elements. We have nuclear fuel, some element that can undergo fission. Usually this is uranium-235. But we also need a neutron moderator. We need something to slow those neutrons down to make fission more likely. Because especially on 235 uranium, fission only happens efficiently if the neutrons are going really, really slow. So we need something to slow them down. Then we need control rods, okay? These are going to be materials that can absorb a lot of extra neutrons to prevent a runaway chain reaction, much like we might see in a nuclear bomb. And finally, we need coolant. We need some kind of fluid, either water or salt, that's going to come through the reactor core and extract heat, and that heat can be used to make electricity. So let's look at each of these in turn. We'll start with the fuel. So when we'll focus on uranium, acknowledging there are many other fuels, but uranium is the most common. Natural uranium is a mixture of two isotopes. So isotopes are versions of the same element that are chemically identical but have more or less neutrons in the nucleus. So for uranium, 238 uranium has 3 additional neutrons relative to 235 uranium. Okay, so 2 different versions. Uranium-238 is much more common. About 99% of natural uranium is uranium-238, and less than 1% is 235. However, 235 uranium is the fissile element. It's the one that fissions most easily. And 238 almost doesn't fission at all. And this is measured by a concept called the fission cross-section, which essentially is the probability an element will fission if it encounters a neutron. Okay? So 235 has a very large fission cross-section, 238 has a small one. So we're left with this problem. If we want to make nuclear energy, we need to enrich uranium into just the 235 isotope, just the lighter isotope. And how can we do that? How can we enrich uranium-235 relative to 238? Well, the first place to start is, where does natural uranium come from? It comes from rock. And uranium ore is commonly mined as pitchblende, which is a mixture of uranium and thorium oxides, or as uraninite, uranium oxide. And it turns out we have a vast global supply of this. We have quite a bit in the United States, a lot in Canada, and a lot in Australia. Plenty of uranium to fuel the world for the rest of our days. But how do we get it from its form in a rock into some enriched uranium-235? This is typically done with a centrifuge process, where essentially the uranium is turned into a uranium hexafluoride gas. It's put into a centrifuge such that the spinning of the centrifuge causes the heavier 238 uranium to go to the outside, and the lighter 235 uranium stays on the inside. We then draw off the uranium-235 through this central tube, and that gas is now relatively enriched in 235. We pass it into an adjacent centrifuge where the cycle is repeated. And if you pass it through hundreds or thousands of centrifuges, you eventually get a uranium hexafluoride gas that is relatively enriched in the lighter isotope of uranium-235. And it turns out that this centrifuge process is non-trivial. And for many countries that are seeking to develop nuclear programs, this is the biggest stumbling block. For example, Iran. So now that you understand something about how the 235 uranium fuel is enriched, let's look at the moderator. How do we slow the neutrons down so they can drive fission more effectively? And we do that essentially by bouncing the neutrons around off of other nuclei that have a very low mass. For example, hydrogen or deuterium. So here's how that works. Fast neutrons come out of fission and they get bounced around, for example, in a moderator made of deuterium. Each time they collide, they dump some of their energy in an elastic collision, and eventually they come out as a slow neutron. Now there's 2 properties that make deuterium a good moderator. One is that it's small, so it can actually exchange a lot of energy with the small neutron. Really large elements essentially act like brick walls where the neutron just bounces off without dumping any energy. So that's one thing. The second thing is that deuterium has a very low absorption cross-section. It's not good at absorbing neutrons, okay? A lot of other materials, like hydrogen, for example, are decent moderators. They exchange energy well, but they tend to also absorb neutrons. And that can really kill the neutron flux that we need in order to sustain a chain reaction. So the absorption cross-section really specifies how likely is an element to absorb a neutron without fissioning. That's the key thing. So now let's look at control rods. Control rods are, in a sense, the opposite of the moderator, where we didn't want our moderator to absorb neutrons, so we wanted it to have a low absorption cross-section. We want our control rods to have a very high absorption cross-section. These are the things that when we lower them in to the nuclear core, we can lower them in and they act like big sponges to suck up all of the extra neutrons and quickly kill that chain reaction, okay? So one example is gadolinium, which has a huge neutron absorption cross-section and can kill that neutron flux very quickly as soon as you slide those gadolinium control rods into the core. So finally, let's look at the coolant. The coolant is the fluid that flows through the nuclear core. It's often water, but it can also be molten salt. And really all this does is heat up. All of this radioactive fission here is dumping a huge amount of heat, and the core gets very, very hot. And so essentially the way we make electricity from this is we pass water or salt through it, which then exchanges heat. The water and salt gets hot, and then we use that hot water to make steam, which then drives a steam turbine, which spins an electromagnet and makes electricity, okay? So we're just using heat to make steam to make electricity. So now that you know something about how nuclear energy works, let's take a look at the Fukushima Daiichi meltdown and think about how this could have been avoided. So this accident happened in Japan in 2011. And essentially we had a large nuclear power plant built right on the ocean. You may know that Japan sits on a subduction zone. There was a huge earthquake which generated a large tsunami. As those tsunami waves came and crashed on shore, they inundated the power plant. So at this point, electricity had been knocked out by the earthquake, and inundation of the power plant by ocean water essentially knocked out the backup generators. So this huge nuclear plant was left with zero electricity. What happened then? The control rods are designed to go back in without electricity. So that was no problem. The rods went back in, fission was killed. However, the nuclear core has so many radioactive fission products that those continue to decay and generate heat even once the fission reaction has stopped. So the core continues to heat up, and it's essential that the core be cooled to avoid a meltdown. Unfortunately, with the electricity being out, power to the coolant pump was lost. However, redundant engineering suggests that these coolant loops should continue to circulate steam and water just based on the pressure of the steam and the hot water itself, okay? Should be a closed loop, and that water should continue to flow through the core even without electricity. Unfortunately, the large earthquake had cracked the containment structure and had essentially allowed this steam pressure in the coolant loop to escape. As the pressure was lost, the coolant water stopped flowing, and eventually two things happened. One, the core overheated and melted the nuclear fuel. Okay, once cooling was lost, the temperature kept rising and it melted down. Additionally, and perhaps more frighteningly, H2 gas built up within the actual reactor building and caused a big explosion, which actually didn't spread that much radioactive material, but was extremely frightening. So we had two things, an explosion and, perhaps worse, a meltdown of the actual reactor core. So this accident really underscores some of the potential dangers of nuclear energy. And it's worth asking the question, what does the future of nuclear energy look like? How could we prevent these kind of accidents in the future? And how could we have the public regain trust in nuclear energy? Well, one thing on the future horizon is a lot of companies are looking into new designs that will improve safety and efficiency over these 50-year-old reactors. For example, one is a molten salt reactor, which it uses a liquid fuel, such that if power goes out, the fuel actually naturally dissipates over into a larger area and is able to get rid of its heat without melting down. Other designs use small modular reactors that are designed to be small and avoid these meltdown kind of accidents. We don't have time to go into these today, but I really urge you to go on your own and research some of these new designs that will improve safety and efficiency going forward. So in summary, nuclear energy produces vast quantities of carbon-free energy. And it does that mostly by nuclear fission, which occurs when an atom absorbs a neutron and splits, releasing a lot of energy in the process. Most conventional reactors have four components: a fuel, a moderator to slow down neutrons, a control rod to absorb excess neutrons, and a coolant to take off heat and use that heat to make electricity. Historically, one of the biggest challenges of having nuclear energy is learning to enrich that uranium-235 fuel and isolate that isotope that actually can undergo fission. And what did we learn from the Fukushima Daiichi accident? That a number of possible engineering solutions can make nuclear energy safer, and a lot of next generation designs may also have something to offer. Thanks for listening, and see you in class.